this is going to be an easy one. Yep, even that guy crashed out in the back of the room is going to understand this. Real simple. Remember last time we had these corresponding angles postulate over here, which said that corresponding angles are congruent when we have two parallel lines cut by a transversal. And then we have some theorems about the alternate interior angles, alternate exterior angles, and the consecutive angles. All of these theorems and the postulate assume that we have two parallel lines cut by a transversal. Now suppose we just have two lines cut by a transversal. We don't know whether they're parallel or not, but we have a burning desire to know, are these lines parallel? One of the things we can use is the analog of the corresponding angles postulate, and that's the corresponding angles converse. This has nothing to do with the shoes you're wearing. Remember what the converse is? That's when you switch the hypothesis and the conclusion. And that's exactly what we're doing here. Over here, two lines, parallel lines cut by a transversal. The corresponding angles that we create when we do that are congruent. Over here, if the lines are cut by a transversal and the corresponding angles that we create are congruent, then the two lines must be parallel, or just are parallel. It's a postulate, so we don't prove it. And if this makes sense to you, then this probably does too. If these two angles weren't equal, that would indicate that these are going to intersect sooner or later, which is exactly what it means to be not parallel. And all these theorems over here just say that you can reverse everything. Here, we've got two parallel lines, and we can make this statement about the congruence of this angle pair. On the other hand, if we can make a statement about the congruence of this angle pair, then the two lines are parallel. Same thing here. We got parallel lines. We can prove something about this pair of angles. If we can prove something about this pair of angles, we have parallel lines. Well, that something has to be that these two are congruent. If you prove something else, I don't think you would end up proving that they were parallel lines, would you? And here, well, these interior angles are supplementary when the lines are parallel. If these two angles are supplementary, then the lines are parallel. I don't think you're going to have a lot of trouble accepting this. Anybody who thinks this isn't true, well, prove it's not true. That's easy to do. Remember, proving something isn't true is usually pretty easy, because all you have to do is find a counterexample. You just find one case where it doesn't hold, and boom, you're done. So, you want to have some fun over the weekend, try to find a case where any of these 6 theorems don't hold. If you do, find a mathematical society and write them. They'll elect you president. Well, this is about all there is to this section. Just using the converse of each of these, this postulate and these theorems. So let's just work some problems and see how this works out. And the best part of this section is that I think, let me double check. Now, the best part of this section is not that I think. That's not what I meant to say. I think the best part of this section, and I double checked, I'm right. The next section is slopes. Slopes are good. You're going to use those all through math. I've already told you how useful they are. And you start start studying slopes, and you're getting into some real mathematics. You can quit asking yourself, gee whiz, why am I studying this? Well, I've told you before that slopes are actually useful in the real world. And all the things we're doing are preparation for these things. So let's take a look at some problems. Here's a problem where we're going to immediately make use of our corresponding angles postulate right up here. These two are corresponding angles, and we want to know what value of x would make m parallel to n. Well, if these two angles are equal, they're parallel. And oh, by the way, did I mention this little, looks like a vertical equal sign? It's pretty graphic. I mean, it's two parallel lines. So if nobody ever told you, you'd probably figure out it's intended to mean parallel, and it's read m is parallel to n. Most of these symbols that you're seeing are not that hard to remember because they kind of look like what they are. In order for these two lines to be parallel, we just set this angle equal to this one. So let's do that. And this is going to be so easy. 3x equals 120, right? So how about x equals 40? 3 times 40 is 120, that makes them equal, so they're parallel. We're done. I told you this section was going to be easy. In fact, why don't you wake up that guy in the back of the room? Let him enjoy this. This is so easy, he ought to enjoy at least one really easy class. And now, since this is going to be a pretty easy lesson, right now I'm going to show you something similar to those error analysis problems that we do. And at the end of the video, I'll tell you the answer. That way you can stop the video before the end if you want to work on it and figure it out for yourself. Here you go. And your job, should you choose to accept, will be to find out what's wrong, or accept it as accurate. I'll run right through this here. We got a equals b equals 1. That's given. So we've just got a couple of variables. They're equal to 1. That means that a squared equals a and b squared equals b. No problem there, right? So a squared minus b squared would equal a minus b. We factor the a squared minus b squared. That's a plus b times a minus b. We've got an a minus b over here, so we can multiply through by 1 over a minus b. That's our multiplicative property of equality. And get that a plus b equals 1. But a is 1 and b is 1, so a plus b is 2. So we have that 2 equals 1. And of course, if 2 equals 1, we can subtract 1 from each side and get that 0 equals 1. And using that, we can add 0 to one side of any equation and 1 to the other side of the equation, and do that as many times as we want. Or we could add 0 to one side of the equation and then subtract 1 from the other side of the equation, because we just decided that 0 and 1 are both equal. We can derive that from the fact that 2 and 1 are equal. And that means anything can be proven to be equal to anything else. It might occur to you that this probably isn't true. If it was, I expect the universe would explode. So what's wrong with it? Well, you'll have to figure that one out. And if I feel like it, I'll tell you at the end of the video. Well, speaking of error analysis, oh, forget that. Come on. I'm tired of these students making mistakes. City councilman. They're always wrong. Just say politician in general. Your congressman concluded that lines A and B are parallel. Describe what that bonehead legislator was thinking. Well, he probably looked at these and said, well, these two are equal and these two are equal, so they must be parallel. all these say this is just what we already know about vertical angle pairs. Vertical angle pairs are always congruent. Doesn't matter whether these A and B are parallel or not. This doesn't say that they aren't parallel, but it doesn't say that they are. Remember, you have to be able to, just saying that they aren't parallel, what am I trying to say? The fact that you can't prove that they aren't parallel doesn't mean that they are. It just means you haven't figured out a way to prove that they aren't yet. You have to actually do something more proactive to prove that they are parallel. Or was it Sherlock Holmes who said, the proof of the absence of a crime does not prove the absence of a crime? Same thing here. I mean, we have the absence of a proof does not prove the absence of parallel lines. Well, if you're getting confused now, just remember that all these are is congruent vertical angles, and that says nothing about whether these two lines are parallel or not. Now here they ask us if there's enough information to prove that M is parallel to N. And of course, the second part is the important part. Explain why. You could just say yes or no and have a 50-50 chance of getting right. That's not mathematics. You gotta say why. Well, remember, these single lines here are intended to imply that these angles are congruent. And what are these? These are an alternate interior angle pair, and they are congruent. And what does that mean? Well, let's see. Don't we have a theorem about that? Oh yeah. It's right here. Alternate interior angles, converse. And so, this is like a one-line proof. The alternate interior angles, converse theorem, implies M is parallel to N, because, well, we haven't even labeled this angle. We call this A and this B, then A is congruent to B. Again, it's so easy, it's hardly even worth mentioning, except that you have to know how to do it so you can do other stuff. That's why we have to mention it. Here's one that, if I understand the problem, it seems to me they're doing it the long way, but maybe they're asking you to do that intentionally, because they're kind of, doggone it, they're not kind of, they are. They just plain are. Asking you to do it in a step-by-step process, which is different from the step-by-step process I would use if I wanted to know if these two were parallel. And let's do it their way and then see if there's another way to show the same thing. And there almost certainly is, because there's usually more than one way to solve a math problem. I think I mentioned that once before, didn't I? Okay, so what's DCG? Well, that's obviously this line breaks up this angle, DCG, into two angles, and we know that the sum of these two angles will add up to the whole angle. So we got 77 plus 38, 115. Now, I would stop right there. We have an alternate interior angles theorem, which says that these are, corresponding angles. Postulate. We don't need a theorem at all. All we need is the postulate down here. Because you can see that DCG and HG, and there's no letter over here, so HG, whatever, are corresponding angles. Boom. Just like these two. That's what these two are. They're equal, so the lines are parallel. But they ask you to do in different steps. So we'll do that. Angle DCG, that's 115. What about CGH? That's this one here. Well, these two form a linear pair. Maybe that's why they're doing it this way, because they don't have a letter out here in order to define this angle. So they got to use this one, because this is the only one they can label with the letters they drew. Makes as much sense as anything else, I guess. So what's this going to be? 65? So this one is 65. Describe the relationship between DCG and CGH. And these are what we called consecutive interior angles, remember? And they do add up to 180, don't they? This is, we already figured out, this is 77 plus 38, which is 115. And this angle here we figured out is 65. So this 115 and 65, they're supplemental, which means these two lines are parallel. That's the consecutive interior angles Converse theorem. So even when you do this the long way, it's pretty quick and easy. Might have been quicker if I didn't talk so much, but you get the idea. Once again, we have something that I think just kind of goes without saying when you talk about math problems. Can you prove that lines A and B are parallel? And if so, explain how. Well, and if you leave out the second part, you can always, again, you got a 50-50 chance of being right by just saying sure or no. I don't know any math teacher who would give you credit for an answer like that. The yes and no part means nothing. You have to explain what you're thinking when you come up with an answer to this. And that's, the explanation is way more important than what you actually come up with. So, what are these two? Well, these are consecutive interior angles. And we know, right here, consecutive interior angles are supplementary if these lines are inverse, or pardon me, are parallel, or if these two angles are supplementary, then A and B are parallel. So all we have to do is check. Does 107 and 73 add up to 180? And you probably don't even need me to write that down, but I will just for fun. 0, 8, 1, boom. They are. So right here. If they're supplementary, that means they add up to 180. So they're parallel. Nothing else to do. Very easy. Now here's one where they're trying to trick you, because these problems are awfully easy, so they got to find some way to try to mess you up, get you to make a mistake. What they're asking about here is lines AD and BC. They're not asking you about these two parallel lines, so let's not confuse the issue. And that's exactly what this person is doing. I don't think a student would make that mistake. I think a city mayor might make that mistake. Yeah. Or how about a King County councilman? Oh, I shouldn't have said that. I should have made it generic. Let's just say a county councilman. I shouldn't cast aspersions on any particular individual, even though he deserves it. The problem here is, although these two angles are congruent, let's see what we really have over here. If this is line A and this is line B, well, the angle, the alternate interior angles are this whole thing here and this whole thing here. Now what happened was this person got confused because they drew in a couple of extra lines which may or may not be parallel, to just confuse the issue and show you that this angle and this angle are equal. Well, that's nice, but they have nothing to do with anything. Not as far as AD and BC are concerned. So that's really where he made his mistake. He's looking at an angle formed with this horizontal line and this transversal, when you want to be considering the angle formed by this line and this transversal. And that's exactly the kind of dumb mistake our King County executive would make, who I can't name because it wouldn't be fair. It wouldn't be fair to the other people who might share that name, is who it wouldn't be fair to. Now here's one where they want to know if you can draw any conclusions from what you see here. And it's really tempting to look at this and say, oh, well, alternate interior angles, these lines must be parallel. Oh, wait a minute here. None of these theorems say anything about two transversals cutting parallel lines. Just one. The alternate interior angle, the other half of the alternate interior angle pair for angle 1, is over here. And for angle 4, it's over here. These two angles really have nothing to do with each other, well, with respect to any theorems or postulates that we have in our tool bag yet. Who carries tools in a bag? That's a stupid thing to say. How about toolbox? A bag of tools would just break, wouldn't it? They'd just fall out the bottom. Can we conclude that P is parallel to Q? Well, how? If we had that this angle was equal to this angle, or angle 1 was equal to angle 3, or congruent, we might have something. But what we have is relationships, or facts, about relationships of angles that involve two different lines, two different transversals cutting R and S. From the diagram, we can conclude that R and S intersect P and Q. We can conclude that angle 1 is congruent to angle 4. With the theorems and postulates we have, that's about it. And those aren't any of the choices, so I'd go with none of the above. We just don't have any theorems that involve two transversals cutting two lines, which would tell us whether anything was parallel to anything. If that's a complete sentence, maybe not. Well, that's about it for this stuff. Like I said, it was pretty simple. I mean, there's how many different ways can you prove the lines are parallel, given what we have today? You're just going to end up using, if you're finding facts about the angles created when you cut two parallel lines with a transversal, here you go. This is the whole thing right here, all on this side here. If you want to know something about whether two lines are parallel when they're cut by a transversal, and you know something about the angles, then this is what you use here to figure that out. There's one whole section right here and another whole section right here. It probably could have been combined into one section if you ask me, but why would anybody ask me? So what about that last one? Or I should say that first one, which I'm going to do last. Or I proved conclusively and without a doubt that 2 equals 1. There it is. Well, what the heck's wrong with that? What'd I do wrong? I mean, a squared equals a, after all. 1 squared equals 1, nothing wrong with that. B squared equals b, makes sense. Now we just subtract one equation from the other. Since b squared is equal to b, we can subtract b squared from this side and subtract b over here. Why? Because they're equal. We're just subtracting equals on each side. That's the subtraction property of equality, as they refer to it. I mentioned before, I prefer to think of it as just the addition property of equality. You either add negative values or add positive values. So this is legal. There's nothing wrong with that. Now we factor this, and if you factor a squared minus b squared, you will get a plus b times a minus b. That's true. Well, now we've got It's a minus b on each side. We multiply through by 1 over a minus b. That's legal, right? We get a plus b equals 1 or 2 equals... Wait a minute. Hang on a second. Our division property of equality comes with a proviso, doesn't it? We can divide through by the same quantity, for instance, anything. Say x. We can divide through both sides of an equation by 1 over x if we have something like a equals b. But what is our big, huge, important, major restriction? X not equal to 0. The division property of equality is bogus if you're going to divide through by 0. If a and b are equal, doesn't even matter that they're equal to 1. The fact is they're equal. That means a minus b equals 0. And what we've done from here to here, see, everything up to here is perfectly reasonable. It's kind of silly when you keep track of the fact that a minus b equals 0. Up here, if you think about this, we've got 1 minus 1 on this side and 1 minus 1 on this side, so we've decided that 0 equals 0. And then we've written that 2 times 0 equals 0 and divided through by 0 to show that 2 equals 0. And we just camouflaged it in a whole bunch of variables and stuff, so that if I wrote that 2 times 0 equals 0, divided through by 0, so obviously 2 equals 1, you'd be throwing wads of paper at the screen right now, and that's just silly. Well, this is the same silliness, but camouflaged. Actually, there was a 1 over a minus b here, too. And I think this is instructive because it teaches you to pay close attention. Don't believe everything everybody tells you just because it makes sense. Go through it, step at a time. You may find, if the conclusion doesn't make sense to you, go back and check it out. You may find that your reticence to accept this conclusion is entirely justified as you go through step by step. You'll probably find an error. In fact, you can find other ways to prove that 2 equals 1. But they're all going to involve division by 0. I found this one on a bathroom wall. Yeah, people write in bathrooms. Well, I was out in the university district, and you know how university people are. Their graffiti's a little bit different. In fact, there was a lot of funny stuff written on the bathroom walls out there, but this is probably the only one I could repeat in the classroom. So, I would say graffiti is not entirely useless. Now and then you see something educational written on the side of a wall. Well, that's it for now. See you next time. And don't forget, we're doing slopes next time.